So welcome everyone to this wonderful series of webinars that are organized under the auspices of UKCRIC, presenting new ideas and the capabilities of the laboratories that have been built as part of the UKCRIC framework. It's my pleasure to talk to you about the work that we have been doing for the last, let us say, 10 years, involving both the pre-UKCRIC lab and the current SoFSI facility. And I'll start with you with some thoughts. Basically, I don't know how familiar you are with earthquake engineering and with keeping communities resilient to natural hazards such as earthquakes, but that's what we're doing. And I'll be very, very pleased to show you around what we have working on the previous years. So wherever in the world, and I mean, let's say in seismic regions, there are specific ways that we have been designing for the last probably 30 years. And this is a probabilistic, basically, way to design structures depending on consequence, on their performance, if you like. So essentially, we have a bunch of criteria saying that if a strong earthquake happens, what is the strong earthquake? The earthquake that doesn't happen very frequently, then the performance of ordinary buildings should be this. But if it is more critical, should be more advanced. And if it is a nuclear power plant, for example, it should be like remain elastic with zero damage. So that's basically the way we are designing things in half of the globe, I would say, which is a seismic region. And this is evolving gradually from a performance-based engineering into what we are calling resilience-based engineering, which basically assessing the consequences first and design to mitigate them in terms of downtime, in terms of functionality loss, in terms of financial loss and the like, and obviously casualties. So this is the new generation of design of structures. Now, the problem while talking about resilience is essentially the fact that resilience is very difficult to be quantified for a number of reasons that have to deal with social and financial factors, how we actually measure downtime, the extent of the loss of functionality. But something that I would like just to draw your attention upon, because it's basic before we start talking about other things, is that resilience is essentially a function of time. It is not just assuming that we're talking about a structure, a network of systems, a network of services, a single person, it doesn't really matter. But essentially, this functionality or operation is, let's say, 100% before the earthquake and drops down to a residual functionality, whatever that is. Then the system, the person, the building, the bridge, London Underground, the network rail, whatever, recovers gradually in time until it reaches the status quo ante, the previous, let us say, state, or even exceeds the previous performance or operation. Now, that happens in between is the loss. And the minimum the loss, the highest the resilience. This is how we engineers tend to quantify or aim to quantify resilience. Obviously, in social sciences, it's a little bit different, but the idea is essentially how can we recover in the minimum time with the minimum resources to the best possible state. Now, some slides from the devastating earthquake that took place about a year ago in Turkey, which was really a very strong experience for those that we visited the place, something that you don't really see very frequently, but it relates a lot to the resilience I was talking about. If you're familiar with the earthquake map in Turkey, but also the geography of the country of Turkey, this is let us call it the East Anatolian Fault, whose rupture essentially led to two very strong earthquakes back-to-back last year. And this is a region of non-seismicity because buildings are designed with requirements that are stricter in the places that you see highlighted in red. So essentially, we're talking about a region that is known for strong earthquakes. And therefore, as much devastating as it is, it was expected, in a sense, to have two earthquakes pretty much in the same region, but measuring really very strong, like 7.5 and 7.8 at a difference of 8 hours. There is a very simple diagram that we're using in earthquake engineering called response spectrum. In the vertical axis is the acceleration that the building is feeling, let us say, experiencing. And because acceleration times mass makes a force, according to Newton, you can understand that's the force induced over the buildings. And on the horizontal axis, you can see the period, or let us say, how high a building is. In red is what the forces for which the buildings are designed in Turkey, with a very advanced seismic code, I have to say. And in gray are the essential accelerations that were monitored during the earthquake. And you can easily see that the red is over-exceeding the gray is over-exceeding the red across a wide range of frequencies and periods, which essentially explains why all these buildings, irrespectively of the height, suffered from heavy damage. Some good news, if we can find good news in this disaster, are seismically isolated hospitals that have performed very, very well as designed, actually. This practically means that buildings are able to slide. There are devices called bearings in a very smooth surface. It's something like a ball that is sliding and is allowing the ground to be moving, but the building not to be experiencing the same accelerations. And then the whole thing is restored back in space. And you can see here some successful operations of this, applications of this technique by the buildings being effectively without a glass broken, whereas other buildings nearby were collapsing. So this is definitely a technique that is very, very promising. The problem is that it's quite expensive. And currently, across the globe, even in developed countries, it is only used for, let's say, critical infrastructure like buildings, hospitals, and some administrative structures that have to remain functional after the earthquake. So most of the buildings rely on the design of their earthquake resistance by means of very strong acceleration, very strong reinforcement. This reinforcement can be very dense, can be very difficult to implement, has a lot of quality control to be ensured, and effectively means that in some parts of the world, yes, you can definitely satisfy these very strict rules, but in other parts of the world, that's what you're seeing. If you walk around places like where we visited in Turkey, but also in Greece, in Italy, in some poor regions, in some places where somehow the quality control hasn't been applied properly, or in places where simply the buildings were old enough, where the new knowledge hadn't been implemented at the time, let's say buildings before the 80s. You can just get an idea. Just to appreciate the level of devastation, entire buildings losing a story, buildings damaged to an irrecoverable state, or buildings tilting like 15 degrees or so. Or other buildings losing their columns, collapsing. It is like a war zone, effectively. This earthquake led to sad fatalities of about 50,000 people and a loss of more than 5 billion to 8 billion US dollars. That can happen in developed countries, like in Turkey. In developing countries, like Nepal, a similar earthquake, effectively in 2015, led to the evaporation of 50% of the GDP in 10 seconds. That's how the earthquake lasted, how long. So in 10 seconds, 50% of whatever the country owned was lost. So the question is, how can we actually implement quality control in these regions where, steel and materials are transported like that, or there's no access to materials, or even they are transported in the way that you see, in ways that do not satisfy the strength or the resistance of the buildings, and the techniques are pretty much, local. So yes, this performance-based design and resilience-based design is a very good idea, but it applies essentially to the developed world. So in low-income countries, the performance objectives are different. So we came up with this idea about 10 years now. What if we don't trust, let's say, the superstructure that will perform properly in case of an earthquake? And for this reason, we create a base where we will let the building rest with the capability to slide. Slide in a natural way, in a low-cost way, in a low-tech way, with materials that can be locally resourced and could be culturally acceptable by the people. Is there such a solution? That would be TRL 1 or 2, I would guess. Let's say the idea, technology readiness level, very, very low. Can we actually do that in reality? People in the ancient world, yes, they thought about it, but in the modern world, how can you apply such a thing? This is the main question. So we had a large project with many, many partners, including also the University of Southampton and the University Caltech and Buffalo from the US, and Nepalese partners, Arab International Development and Save the Children. So we started studying first the materials. I'm not getting into too much detail. I just want you to get the feeling how we can turn an idea into practice through large-scale experimental testing. So the idea here is that first you have to trust the local people. Let them build in the way they normally build. Don't try to mimic this and bring it to the UK and think that you can do it in the same way. You can't do it in the same way. So we did it locally in Kathmandu. We tested it locally. You can see here even the manual way forces are applied. At some point, obviously, if you apply too much force, these walls will effectively fail and collapse. And if you repeat it many times, you will be able to assess the capacity of this type of construction. Because if you really want to improve something, you have to understand it. You go there, you react, you collaborate with the local people. There are too many things you can learn. Then you go back to the UK in this case. And we said, what if we rest a small building that's a very, very small steel box, if you like? Let's rest it on sand mixed with some chalked rubbers, which is very cheap to do. Would that building really slide, or this box really slide if we shake it? Would it? Well, yes. So in principle, it's working. But the bad news is that at the end of the day, it is also tilting a lot. Maybe you can observe it even visually. So in mathematics, everything works beautifully, and you can say that because the system slides, there is a cut-off acceleration. There is an upper bound of the energy that gets into the structure, which is the red one. So you're applying the blue, and the building is experiencing only the red. So you're doing good. But if you end up with tilting, if you end up with settlements, if you cannot use your structure anymore, what's the point? So we had to try different ways and do this proof of concept at a large scale. This is the laboratory before the UKCRIC that equals shaking table in the earthquake lab in Bristol. It's a 3x3 shaking table, 6 degrees of freedom with 8 actuators. You can place on that a payload of about 15 tons and accelerate it up to 2G. So that's about twice the earthquake measured in Turkey. So this is very, very large, I would say. And you can do that for 6 degrees of freedom, 3 translational, 3 rotational. But with the aid of UKCRIC, we built a new lab, which I think is way more powerful. And I would like also to say a few words about this, because this not only has 3 degrees of freedom shaking table that is larger, but also has a soil pit for tests that involve soil structure interaction. The good thing about the shaking table is now that the payload is about 50 tons. That's, let's say, the weight of around 30 cars, okay, stacked, the one on top of the other, and you can accelerate that as well up to 2G for a frequency that ranges from 1 to 50 Hertz. So this is really very, very powerful. And in this laboratory, we can test things that relate with structural dynamics, geotechnical engineering, soil structure interaction, everything from small scale to large scale, from a single hazard that is earthquake, but we can also have an environmental chamber and use some water that is flowing into the soil pit. We can test multiple hazards. We can reproduce to some extent floods. We can test smart materials. Overall, we're looking at the resilience of critical infrastructure. You can see how the shaking table looks like and pretty much how it is moving in 2 dimensions. In this case, this is really a very, very powerful tool. Currently, we are testing through new projects that we brought 3D printed units. We are testing buildings designed with new materials. We are testing structures that are effectively placed into this large shear box filled with sand to include soil structure interaction in our analysis. Whatever involves dynamic loading and whatever involves a case where the loads come from the bottom to the top, that's the shaking table. In case we need to test something to very high accelerations like 10G, that in that case, we are going to be using the hexabot, this mini monster, which can go up to very high accelerations, as I mentioned, for specimens that are smaller, like components of structures located in high-rise buildings, aeronautics or mechanical devices, and other protecting schemes. And of course, we've got the soil pit, which is a 6 by 5 by 4 meters underground room, if you like. We can apply forces from the side, lateral forces, using large 1 meganewton actuators, or we can mount the actuators on the strong floor, or we could place and create a reaction frame around the soil pit and apply forces from top to bottom. So whenever we would like to test something like this, this is an excellent example of test that we run with the University of Southampton and the University of Birmingham as part of Plexus Plus, which was also funded by UKCRIC, and we're grateful for this support. We run thermal tests, contraction and expansion of integral bridge abutments, filling the pit with sand. You can see also here how the sand was transferred, how the loads were applied, how does it look like when you push laterally. Everything is instrumented with fiber optics, with pressure cells, and with all the instrumentation you can get. Now we can do that statically, we can do that dynamically. We can test here wind turbines that are supported on sand conditions. We can test floating turbines if we would like to introduce water because there is drainage in the system. We can do hybrid testing, that's substructuring, and effectively we're preparing now a fantastic test on timber buildings, which is very interesting to do by applying lateral wind forces externally. So these are the new capabilities that we would love to welcome you all to visit and explore possibilities to use of the new facility. But in the meantime, I'm just thinking back to the previous laboratory for one simple reason. Because the tests we were running were involving the vertical component of the motion as well, since this gets into the calculation of the sliding, and therefore we had to do it in the equals shaking table, which has 6 degrees of freedom of acceleration, including the vertical. For this reason, you can see that we did these tests in a larger scale compared to the small box where we were looking at. But effectively, what we learned from this is that, again, it's working very nice, but you end up with some permanent tilt, which is never a good idea. So the question was, can we do it differently? Can we actually have a sandwich of plastic, sand, and plastic, and also concrete on top and concrete at the bottom? So it's concrete, plastic, sand, plastic, and concrete. That's the sandwich. And this controls very well the sliding to take place at this specific sand interface. But from this idea into running this test, it was always a challenge. I already told you how challenging it is to convert an idea into something tangible. But you can see here that this time, if you let it slide, it slides, you're going to see it in a while, yes. It slides in a very controlled way across a very specific interface. And this gave us the advancement, if you like, to reach technology readiness level 4, which means that not only the proof of concept is working, but technologically it can be reliable enough to design further the details. And you can also see here that you are applying the motions, the displacements in blue, and the building is basically doing what you see in red, which is leave some permanent displacements, but in terms of acceleration that relates to the force, the red is always capped at the time that the system is sliding. So without sliding, it would do the blue acceleration, but with sliding, it can only do the red, which is always doing good system, I would say. So another question was, what is the optimum friction coefficient? That's also an experimental question. And we had several tests that we did using also rollers on the sliding surface with different densities and different sizes. And we also had a very extensive set of numerical probabilistic assessment of buildings mimicking the properties of these buildings. You can see, for instance, on the left, the prediction of an ordinary building that effectively becomes red and collapses because all the first story is lost, whereas the sand building, the PVC sliding system, let us say, remains without collapsing. So these are just some illustrative examples and some technical metrics that we have to compare. When you see a lot of hysteretic behavior, that's a lot of damage. That's what the black line tells us here in the moment rotation damage. When you see the green one, which is very, very slim, this means that there is no absorption of energy, therefore there is no damage. Therefore, that's a way, way, way better to protect the building. And it's low cost. And after all, it's quite effective, because if you do this probabilistically and take the mean, which is the, let's say, the solid black line of a conventional building, with the dotted lines being plus minus one standard deviation of the damage of the building, that's what drift shows in the vertical axis. Essentially, the red one, which is the isolated in a low-cost way, always has way lower damage. Again, I'm going to skip these slides that are perhaps too technical for this purpose, because that's not the purpose of this talk. Just to say that for clarity, this low-cost system, once it slides, it is not able to be recentered, because effectively the earthquake has led the building to, be displaced for like 10, 20 centimeters, and then it's not returning to its original position. However, we have now received funding in the new lab this time, so I'll be very glad to show you this when it's done, two tests for low-cost seismic isolation that has another low-cost mechanism to recenter. In the meantime, and I will close with these slides, I would like to share with you how we converted this idea into actual construction. So we have been working the last 4 years with the government of Nepal and the Ministry of Education. We have been allocated some space in a school courtyard, and there we have designed the foundations. We have redesigned a new school. The University of Bristol funded the construction of that school. We tested extensively all sorts of sands that we could get from the local rivers in Kathmandu. These sands were packed and sent into Bristol. We were testing to identify the friction coefficient, different sand density, different water conditions, different vertical pressures, different angularities of the grains, everything you can imagine. We were testing in small scale, in the shear stack, in large scale. We did a very extensive work just to verify that essentially the friction coefficient remained reasonably stable so that we could use it. And then we designed the building to be effectively not embedded into the ground, but resting on the soil, with a parapet having a gap of about 35 centimeters, a parapet that is sacrificial. So just in case the earthquake leads the building to slide, then this parapet is actually going to be sheared off, and it's going to be just reconstructed after the earthquake, because that's not a problem. These are the key parameters of the problem, involving obviously mechanically the friction coefficient and what we call in earthquake engineering the behavior factor, which is the degree of absorption of energy that's compulsory to account when you're designing structures, and also what is your performance objective. Some photos just to appreciate how this new school looks like. Actually, that's the first building in the world that has been constructed with this technique. And it was materialized by our Nepalese partners. So we tried to make it so simple that people could do, and effectively they did it in a very meticulous way. This was taken care by the National Society for Earthquake Technology in Nepal, the governmental scientific institution. They did beautiful work in setting up the level foundation. Then in introducing the PVC sheets, as you can see here, the video, cutting the PVC sheets very, very carefully according to the guidelines, and then after sieving the sand, they were applying the densities. It doesn't really matter whether the density is exact or a little bit higher, a little bit lower. It's a protective mechanism. It's only doing good on top of what we would do anyway for the earthquake design of a building. That's how the plastic sheets are laid. And you can see here how our colleagues and workers have been working. And this is how it looks like after it was finished. And that is the gap. During construction, you can see that this is the PVC system at the base of the foundation. So if an earthquake happens from a threshold of acceleration and upwards, it's going to slide and it won't be damaged, simply because it is protected from very high accelerations to entering the building. And that's how the construction progressed and how it looks like. And this is essentially the current state. We're waiting to get additional funding to monitor the building, but also to build a second story. So I hope that the kids were quite happy to see that. And I would like to acknowledge all my colleagues for helping us with this effort, particularly our colleague Nick Alexander, that unfortunately left us, which was the pioneer and a very, very important person in this endeavor, along with the other colleagues and the World Bank who supported this project. So as a closure, I would like to say three other things that I believe were needed to translate an idea into something real. One was to have the large-scale capabilities to be able to see things, because scale matters, clearly. The second is to have local collaboration with people who are able and willing to deliver this technology. And the third level is to have, obviously, the scientific background to understand how to translate something that is mathematically specific into physically possible, and also something that it is technically complex into low tech. If you manage to bring these three circles into one comprehensive approach, then it is possible, after some years, obviously, to convert your ideas through an exciting journey, really, into something very, very pragmatic. So with that, I would like to encourage you as you are early stage careers, if you have an idea, think it all the way. Not just about writing a single paper, not just about, going from one equation to the other. This is needed. But if you really want to have impact, you have to take it all the way. And it's always a fantastic exercise to do it straight on from the beginning. It doesn't matter if you change it down the road. It is important that you have a plan. A bad plan is better than no plan. That's my humble advice. And with that, I would like to close my presentation. And thank you once more for the kind invitation.
Thank you very much. That was a really very interesting presentation. I am not technical in any way, shape or form, but I very much enjoyed seeing kind of how the ideas went from the lab to the kind of real life environment. And I think you're absolutely right about working with kind of the local people, the expertise, the kind of the local materials, to make sure that you are kind of co-creating with them. And I presume that the plan would be that you would go ahead and build more buildings like this should it be successful. Is that the case?
That's exactly the case. Plus that our dream is that we don't build them, the Nepalese do, because we need to empower the communities so that they know they don't need us. That's the whole approach. You're transferring the know-how and you're empowering them. And we are hoping that we will organize an international workshop this year where the Nepalese will be showcasing to the nearby communities and countries this new technology and how they were able to do it in Bangladesh, in Bhutan, in northern India, in Pakistan, and other countries in the region. We are very, very happy that we met these people. Personally, I learned a lot, honestly, and I feel very, very pleased that we had this opportunity.
Yeah, I think that's the case kind of with all knowledge exchange. It's about that kind of conversation between partners and being able to kind of root out the preciousness of each person's kind of contribution and kind of bring that through to a final project. Does anyone in the room have any particular questions or comments that they would like to make? Susie, thank you.
Hello everyone. Hi Tasos, thanks for such an interesting presentation. I'm coming more from a social science background, and so really interested in sort of how technology becomes locally adapted and then taken up, and I wonder if you could shed any more light on what you think the steps are that the Nepali authorities and construction industry might take that forward.
That's an excellent question, Susie. I think for such large-scale efforts, you do need to have the support of the local government. But that's not enough, because you also need people who are talking the same language, the technical language. So we were very pleased that we had the blessing of the government and the Ministry of Education from the beginning. But at the same time, we had colleagues that were really very well qualified, and they were able to produce, as Jenny very rightly stressed, to co-create the ideas. You cannot just go in a place and say, hey, I have these nice ideas, they will work for you. No, they have a better idea what would work for them, actually. So you have to listen a lot. And we made several workshops in between, involving also social scientists, I have to say, to have a set of activities. I presented the technical activities, but we also had community engagement meetings. We tried to assess the resilience at a community level. What makes you stronger against future events? What are you afraid of mostly? What is your social structure? What is the coherence of this village in relation to the other village? What is the backup plan? Do you have this? Do you have that? And we have a framework now for that. It wasn't the purpose of the talk to present, but I think that this part helped us tremendously in the technical part. First, because we understood the context. And secondly, because the people started talking to us, trusting us. They don't know you. They have no reason. We asked them initially, what is you think is the main hazard? An earthquake was number 5. Why? Because they were smart enough to know that the earthquakes don't happen every day, but the cold will come next winter, but the thunderstorm will come next week. So these are things you need to learn. And therefore, I don't know if I'm allowed to say that on record. I think the UKCRIC Global Challenges Fund will be happy to hear. But what we actually delivered was kind of different to what we had initially stated in the proposal, in that it was influenced by the local people. And we're very proud that we had the signature of the local community in the final outcome. Otherwise, they wouldn't have embraced it, I think.
Thank you. Yeah, that sounds like a really good approach and a sort of best practice way of doing things. Thanks for the insight.
Thank you, Susan.
Joanne.
Hello,
Anastasios.
So my question was actually around advice you might be able to give to early career researchers and maybe people interested and new to this sort of thing. And in particular, you talked about some substantial labs. The UKCRIC SoFSI lab, is a big and expensive and impressive facility. And also you talked about traveling overseas and engaging communities, and these can feel very daunting process-wise, even if kind of with very good ideas and lots of energy. But this combination can be very daunting, especially for early career researchers. And I wondered if you had any advice around that.
My advice, I don't know if it is right or wrong, but my advice is think big and then join a group that has the ability to help you in your first baby steps. So don't get isolated. Talk to your colleagues, talk to the people around you, attend workshops, attend events that are not relevant to what is your main field of expertise. Get transferable ideas from elsewhere. Open your mind. Then life will bring you at some point at the position to be able to implement big ideas. But this requires some mental preparation, I have to say. The most important projects are multidisciplinary. The most challenging problems are multidisciplinary. So even if it feels daunting or it feels, oh, that's impossible for me to do, well, yes, but we have been early career researchers also. So we never thought that this would be possible. But working year by year, setting tangible goals, have a roadmap. Where would I like to be in 5 years from now? This doesn't, you were not, wizards to know, but we can just say, well, I would like to be in the industry, or maybe not. I want to be in the academia. I want to be working internationally or nationally. I want to work in the office. I want to work in the field. I like geo, I like structures. I like this, I like that. So have an idea. Don't let the flow take you anywhere. That's my advice. Set a plan. Life will change this plan millions of times, that obviously, but I think that engaging with others, particularly with people who are of the same mindset that you think would serve your plan. So if you resonate with the appropriate group, you will easily go with the flow. So my advice to summarize is think a little bit. You are young, but you are very smart. So think a little bit about where you want to go, how you would like to change the world. It's not so, it is difficult, but it is possible after some years.
Thank you. Thanks, Tassos.
Thank you. Are there any other questions or comments that people would like to kind of raise at this point? Okay, well, thank you very much to everyone that's here. Most to Tassos, thank you so much for your presentation and your wise words there. It's really very encouraging. Yes, good luck with all the rest of your kind of the research, and we hope that more of these buildings are seen in the future, because yes, it definitely seems like excellent research to have some useful impact in those communities. So yeah, watch this space. I think it is in those.
Thank you very much both for the kind invitation. And if any of the people who see the video would like to send a question, feel free to reach out. We'll be very, very happy to help. The younger you are, the better chance to get a very, very quick answer.
Yeah. Perfect.
Is it younger though, or is it just not worn down by your discipline and your colleagues?
Yeah, you know better.
You can be early to it.
Exactly. Very happy to help in any way.
It's great. Thank you to everyone who was here present in the room, and to those who are watching the recording. We have a few of these sort of presentations, webinars every year from the different areas of kind of the UKCRIC facilities and expertise. So look out for our next ones coming up in the next few months. And if you have any suggestions of people you'd like to hear from, then please feel free to drop me an email, and we can arrange for them to be contacted and drawn out too. So thank you very much, everybody, and have a good rest of your day.
Thank you very much. Bye-bye.
Thanks. And thanks,
Goodbye.
Jenny.